to use the simplex method and the duality principle to solve a minimum problem. So remember, with the simplex method, we have to modify the method a little bit to solve a minimum problem, whereas with the geometric approach, the same approach would give us both the minimum and maximum, but with the simplex method, you saw how the method works for solving a maximum problem. Now we're going to modify that same method just a bit, maybe 10 or 15%, in order to make it suitable to solve a minimum problem. So before we talk about the minimum problem per se, and then first we have to talk about a matrix operation which we haven't yet talked about, and that's how to take the transpose of a matrix. So suppose we want to obtain the transpose of a matrix. It's a very simple operation. So if we have, the best way to explain this is just jump right into an example. Suppose we have a matrix such as 3, 4, and 2, and negative 8, right? And let's call this matrix A. The transpose of this would be a matrix called, the way we labeled or denote a transpose matrix is the letter A with a capital letter T in the upper right corner. So that's transpose of matrix A equals the first row of the original matrix becomes the first column. So 3, 4. The second row of the original matrix becomes the second column. So 2, negative 8. Let's do another example. Suppose we want to transpose this matrix. Let's make it a 3 by 3 matrix. So we have 8, 9, negative 3, and then 0, 2, 4, and then 11, and say 5, and negative 1, right? We want to take the transpose of this. So once again, let's call this matrix A, and then the transpose matrix is going to be the first row becomes the first column. So 8, 9, negative 3. The second row becomes the second column. And the third row becomes the third column. Okay, so that's the transpose. Let's give a couple of more examples and then we are set. So suppose we want to transpose this matrix. 1, 9, negative 5, and 24. Yes, so that. And let's call this A equals, and then the transpose matrix, let's see, so we have, so A transpose, we have 1, 9, negative 5, and 24. So the first row is 1, it becomes the first column. The second row is 9, it becomes the second column. Third row is negative 5, and it becomes the third column. Fourth row becomes the fourth column. Okay, so, or if you had, the opposite of this is true. So if you were given this as the original matrix, you would take the transpose by going this way. So you would rewrite this in this form. Okay, So that's basically the transpose of a matrix. So now let's ask an overall question. With the duality principle. Work. How does this method work? It has two main steps. And by the way, all of this is for standard minimum problem. So as we said in discussing sections 5.1 and 5.2, in this course, we are not covering non-standard simplex problems. It's just standard maximum problem and now a standard minimum problem. So first, we obtain the dual problem. We're going to learn how to do this in this section. And then we're going to using the duality principle. So let me quickly add something very important to this. The dual problem is nothing more than an equivalent maximum problem. So originally we start with a minimum problem. We have to obtain the dual problem for that original minimum problem. What's a dual problem? It's a maximum problem that is equivalent to the original minimum problem. Okay, so this dual problem is the IE and equivalent maximum problem. Okay, all right. So it is in this step, in obtaining the dual problem, when we need to use the transpose of a matrix. Okay, let's see how that works. I think it's a good idea to first talk about because we talked about how the standard form of a maximum problem looks. It's a good idea to also see how the standard form of a minimum problem looks. Okay, so let's do that. So this is what the standard minimum problem consists of. One, all variables must be positive, just like the maximum problem, right? This was the same thing. This is where we have the x1 being greater than or equal to 0, x2 being greater than or equal to 0, and so on. So x1 greater than or equal to 0, x2 greater than or equal to 0, and so on. And so on. So that's the first condition for having a standard minimum problem. The second condition is So all constraint inequalities must be greater than or equal to a positive or a negative constant. Remember, with the maximum problem, it was all constraint inequalities must be less than or equal to a positive constant. So the first one is the same as for maximum problem. The second one is drastically different, right? There's another third and last condition for standard minimum problems, which is, again, this is very different than for the maximum problems. So we have the coefficients of the original minimum problem, minimum objective function must be positive. Whenever I talk about this in class when everybody's present, people ask me, so can you have negative coefficients here? Yes, absolutely. You can have in the constraint inequalities the coefficients of the variables x1, x2, and so on can be negative. But here in the objective function, the coefficients cannot be negative. They have to be positive. The coefficients in the of variables in the objective function must be positive. Okay, so let's see how this looks in an example. So minimize. Here's the objective function, c equals. You usually see, or I think exclusively, C used in your textbook for the section on minimum method. It's because if we're minimizing an objective function, it's usually the cost function. So C stands for cost. C equals 4x1 plus 2x2. Okay, so that's notice that the coefficients are positive, right? And on subject to these constraints, which are negative x1 plus 2x2 greater than or equal to negative 2, 2x1 plus 3x2 greater than or equal to 6. And of course, we must have x1 greater than or equal to 0, x2 greater than or equal to 0. So that's a standard minimum problem. The objective function has positive coefficients. The constraint inequalities are greater than or equal to either a positive or a negative constant. So these must be greater than or equal to, not less than or equal to, like you saw with the maximum problem. And here the coefficients can be negative. Not here, but here it's allowed. So let's understand how we can obtain the dual problem for a minimum problem. Okay, so we want to do first, again, guys, this is, it's given that this is the dual problem of a standard minimum problem, right? Let me emphasize that. It will be different for a non-standard problem, which we will not talk about in this course. So write a matrix of the coefficients in the top rows and at the bottom. So the original matrix of coefficients we write down. The top rows are always the coefficients of the constraint inequalities. The very bottom row are always the coefficients of the original objective function without any rearranging. Remember, in the maximum problem, we had to rearrange those coefficients, right? Move them all to the left and set the entire objective function to equal to 0. In here, that's not how we begin. This is how we start that. And you'll see examples of how this works. And then 2. So that matrix, in the second step, we take the transpose of that matrix, in part 1, above. We take the transpose of that, and let me add right at the end of this that once you take the transpose, you now have the coefficients of the new variables. New variables y1, y2, y3, and so on in the dual problem. So those numbers that you get when you transpose the matrix, original matrix, those are the coefficients of the new variables y1, y2, y3. So you're at this point, after you take the transpose, you're no longer dealing with variables x1, x2, x3. You have new variables y1, y2, y3. These variables belong to the dual problem, which is the equivalent maximum problem. And in this third step, create the dual problem, and then finally and I'll just add equivalent maximum problem, then set up the initial simplex tableau. And solve. So, but that will be part of solving the dual problem, which at this point we just want to know how to set up the dual problem. So probably this would be the step after that. So obtaining the dual problem will end here actually in step 3. Okay, so let's do a couple of examples where we're not going to solve the minimum problem. We're just going to set up the dual problem, because if we don't know how to do that, then there's no point of discussing how to solve that, how to solve a minimum problem. So let's first make sure we know how to set up a dual problem. Here's an example to help us do that. And let me add quickly, do not solve the dual problem. Okay, here's the minimum problem. We want to minimize this objective function subject to these constraints. Okay, so the first thing is that let's write down the initial matrix of coefficients. With these coefficients in the top rows, right? So 3, -1, and 4. And then 1, -2, and 3. These are just the condition that all variables should be positive, so that we don't bother with that. But now these coefficients, we will bring them here as they are without rearranging. So 3, then for x2 we have 5, and then of course 0, always 0 in the last column at the bottom row. So this is our objective row. These top rows these numbers are coming from the constraint inequalities. Okay, so this is our original matrix of coefficients. We need to take the transpose of this in the minimum problem. And we will have the first row becomes the first column, right? Second row becomes the second column. And the third row becomes the third column, like that. So these numbers no longer have anything to do with the original minimum problem. These are new variables. So these are not x1 and x2 anymore, so this has to be y1. These are the coefficients of variable y1. These are new variables. And these are the coefficients of variable y2. And these are the constants on the other side. So let's use these to write the objective function and the constraint inequalities for the dual problem. Remember, the dual problem is a maximum problem. So all the constraint inequalities should be less than or equal to, no longer greater than or equal to, less than or equal to. Okay, so we can do that by writing that 3y1 plus y2 less than or equal to 3. Right? Now this one, minus y1 minus 2y2 less than or equal to 5. And the bottom row, these numbers belong to the objective function. So let me write them here. So P equals 4y1 plus 3y2. That's our objective function. And of course, we have y1 greater than or equal to 0, y2 greater than or equal to 0. So this is the dual problem. Which is a maximum problem. Okay. I'm sure you have questions about this. Please post them right underneath the video on the discussion board. Let's do another example. In this next example, we're going to do the same thing. We're going to set up the dual problem, but not solve the minimum problem yet. Okay, here is this minimum problem. We want to minimize subject to these constraints. We have 2x1 plus x2 like that. Okay, so once again, we begin with the initial matrix of coefficients, with the top rows being the coefficients of the constraint inequalities, and the very bottom row, the coefficients of the objective function. So we have 2, 1, 1, 1, and then 80, Notice these are the coefficients of the original variables x1, x2, x3, x4. When we take the transpose, the new variables are y1 and y2, no longer x1 and x2. Okay, these coefficients, 2, then 3, then 1, then 2, and then 100. And finally, the bottom row, it's going to be the objective function. 2, right? 1, 4, 1, and then 0. Always in this corner, 0. Okay. Now, we are ready to take the transpose of this, right? Let's do that. So the first row becomes the first column. We have 2, 1, 1, 1, 80, then 2, 3, 1, 2, 100, and then 2, 1, 4, 1, 0. So notice that these are now the coefficients of variable y1. These are the coefficients of variable y2. And these are the constants. So let's use these new variables and numbers to set up the dual problem. So from this, we know that we have 2y1 plus 2y2 less than or equal to 2. From this row, we have 1 times y1, right, which is y1 plus 3y2 less than or equal to 1. Then y1, 1 times y1 is y1, 1 times y2 is y2 less than or equal to 4. And then again, y1 plus 2y2 less than or equal to 1. And from the last row, these guys, these are the coefficients of the objective function, which is p equals 80y1 plus 100y2. All right, and finally, y1 greater than or equal to 0, y2 greater than or equal to 0. So this is our dual problem. Okay, so the next example, we're going to solve a minimum problem from beginning to end. We're actually going to do 2 examples of solving the minimum problem from beginning to the end. But notice that these are maximum problem. The dual problem is a maximum problem, so everything is less than or equal to. Okay, just remember that. So from this point forward, it's all the same as the maximum problem, except at the very end when we have the final tableau. Once we have the final tableau, then the values of x1, x2, x3, x4 are obtained from the slack variables. That's the main difference between this method and the method that you saw for the maximum problem. So we obtain our solution of the variables x1, x2, x3, x4 from the slack variables, not from the non-basic variables y1, y2. We get the solution of the minimum problem from the slack variables. So you'll see how that works when we get to that point. So here we want to solve using the duality principle. Okay, so here's the problem. We want to minimize this objective function 3x1 plus 4x2, which is subject to these constraints, which are x1 plus x2 greater than or equal to 3, 2x1 plus x2 greater than or equal to 4, and x1 greater than or equal to 0, x2 greater than or equal to 0. Okay, so in fact, even though this is the first problem, it would be a really good idea for you to pause the video, find the dual problem, solve it, or go all the way, set up the initial simplex tableau after that, and find the final tableau, and then come back to the video. It would be a very good exercise to do that, because you will find all the spots where you are likely to make any mistakes. You'll catch them that way. All right. So first I'm going to write down the matrix of the original coefficients, which is this. We would be 1, 1, 3. It would be then 2, 1, 4. And then we'll have the objective variable coefficients are 3 and 4. 3, 4, and 0. Okay, so let's take the transpose of that. The first row becomes the first column. The second row becomes the second column. And the third row becomes the third column. Okay, so we're going to write the dual problem using this. Recall, please, that these are the coefficients of new variables y1, and these are the new coefficients of variable y2, and the other side is just the constants. So the dual problem is as follows. We have y1 plus 2y2 less than or equal to 3, right? Because this is the dual problem is a maximum problem. So less than or equal to 3. Then y1 plus y2 less than or equal to 4. And from the bottom row, we have the objective function, right? From these numbers, we have p equals 3y1 plus 4y2. And of course, we know that y1 is greater than or equal to 0, y2 is greater than or equal to 0. All right, so now, this being our dual or maximum problem, we can set up the initial simplex tableau. And just like the sections 5.1 and 5.2, we can go about solving this. But instead of x1 and x2, we have y1 and y2. Okay. So initial simplex tableau was, first we start with variable p, then the non-basic variables, which are y1 and y2 in this case, then the slack variables, which are S1 and S2. Right? We have two constraint inequalities, so we're going to need two slack variables, and then of course the right hand side, like that. So I'm going to put a P on this side. Okay, we know that the first column is 0, 0, 1, right? From sections 5.1, 5.2, we know that. Now, the coefficients here would be 1, 2, S1 would be 1. That's the slack variable needed to convert this first inequality into equality, right? So 1, and then 0, and then 3. For the second inequality, we have 1, 1, 0, 1, and 4. And finally, we need to, since this is a maximum problem, remember, before we use these coefficients of the objective function, we need to move them, right? We need to rearrange these such that we have P minus 3y1 minus 4y2 equals 0. These are the coefficients that we are importing into this. So we have minus 3, minus 4, and 0 the rest of the way. Okay, so just like what we talked about in sections 5.1 and 5.2, our pivot column is this one. So both of these numbers are positive. We need to find the smallest ratio, right? So let's do that. So 3 divided by 1 is 3. 4 divided by 1 is 4. This is the smallest ratio. So that means that this is our pivot element, right? We need to keep that, which is already 1, which is great. We don't have to do anything to this to convert it to 1, but we need to make these two numbers equal to 0, right? So let's do that. So the row operations for doing that, and also please remember that the first row is the pivot row, right? That is our pivot row. We're going to use row 1 to convert 1 and negative 3 to zeros. So let me write down the row operation for doing that. So to convert this 1 to 0, all we need is add a negative 1 to it. Where is the negative 1 going to come from? It's going to come from multiplying the first row by negative 1 and adding it to this one. So row 2, which is the row we're going to change, is equal to minus row 1 plus row 2. Then how are we going to convert this negative 3 to 0? All we need is a positive 3 to add to this, to get it to 0. So where is the positive 3 going to come from? It's going to come from multiplying the pivot row, the first row, the pivot row by 3 and adding it to the third row, and that way we can get the negative 3 to be 0. So row 3, which is the row we're going to change with this operation, is 3 times row 1 plus row 3. Okay, so let's write down the next tableau. We have P, Y1, Y2, S1, S2, and the right-hand side column. And here's the P here. So 0, 0, 1 is the first column. The first row isn't going to change. This row isn't changing because it's the pivot row, right? So I'm going to write it as it is. Now let's do this row operation first. So multiply the first row by -1 and add it to row 2. So minus 0 is 0 plus 0, we got it, 0. Minus 1 times 1 is 1, plus 1, plus positive 1, 0. Minus 1 times 2 is minus 2, plus 1, minus 1. Minus 1 times 1 is minus 1, plus 0 is minus 1. Minus 1 times 0 is 0, plus 1 is 1. Minus 1 times 3 is minus 3, plus 4 is positive 1. So let's do this row operation next. This is telling us to multiply the first row by 3 and add it to row 3. So 3 times 0 is 0, plus 1, 1. We already have it. 3 times 1 is 3, plus -3, 0. 3 times 2 is 6, plus -4, that's positive 2. 3 times 1 is 3, plus 0 is 3. 3 times 0 is 0, plus 0 is 0. 3 times 3 is 9, plus 0 is 9. Okay, look at this. We've already found the final tableau. Okay, so now the interpretation of this final tableau is very different than the interpretation of the final tableau for the original maximum problem. So let's see how we can interpret this final tableau. This is our final tableau. Okay, so here the S1 gives us the value for x1. So that is S1 gives us the value for x1 in the objective. The value of S1 in the objective row in the final tableau gives us the value of x1. The value of S2 in the objective row in the final tableau gives us the value of x2. So the original problem, minimum problem, has these solutions. x1 equals 3, x2 equals 0, and c, which was the minimum problem variable, is minimized at 9, which is that. So the interpretation of the slack variables is different, but the value of the minimum problem, the value of the objective function at minimum is still found in this corner. This was the case for the maximum problem as well. Remember that? So for the minimum problem, the value of the minimum, the value of the objective function at minimum is also obtained in this corner, which is that. Please don't forget to post your questions right underneath the video on the discussion board. So let's do another problem. Okay, so here we have, again, to minimize this objective function and subject to these constraints. And so we have these three constraints. So we have that, and of course the requirement that all three variables have to be positive, right? So we have that like that. Okay, so of course I want to ask you to, again, please pause the video before you see my solution. Write down your next step, what you would do, and then unpause the video and see what I've done with this whole solution. That would be ideal for learning this topic. Okay, so I'm assuming you've done that and you already have your solution at the ready. And let me go about and doing the same then. Hopefully our answers agree. So we have first we have the initial matrix of the coefficients. So we have 1, -2, -3, -2. Let's write those down. Then we have 1, 1, 1, 2. Then of course here we got to be careful because there's an x1 but there's no x2. So for x1 the coefficient of course is 2, but there's no x2, and I should have written this a little bit higher to leave myself room for the coefficients of the objective function, but it's okay. So we have 2, there's no x2, so 0 for that coefficient. And then of course we have x3 with coefficient 1, and then the other side is 3. Okay, so these coefficients from the objective function as they are, let's import those into the initial matrix of coefficients. So we have 2, 3, right? 2 for x1, because these are the coefficients of x1 in the inequalities first, then the objective function, then x2, these are the coefficients, then x3, then of course those are the constants. Okay, so we have 2, 3 for x2, for x3 it's 4, and of course for the constant we take that as 0. Okay, so now as you saw in the previous examples, we have to take the transpose of this. So taking the transpose, we have the following matrix. Let me move this up a little bit, like that. Okay, so we have the first row becomes the first column in the transpose matrix. 1, -2, -3, -2. Then the second row becomes the second column. 1, 1, 1, 2. The third row becomes the third column. 2, 0. Right? So it's 2, 0, 1, and 3. And of course, the last row becomes the last column. So 2, 3, 4, and 0. So these become the coefficients of the maximum problem in the dual problem. The coefficients of variables in the dual problem, so to speak. So let me label these. So this column becomes the coefficients of y1. The second one becomes the coefficients of y2. And this would become y3. And of course, these are the constants. Okay, so let's write the dual problem using these coefficients, right? So these are our new variables. The dual problem is a new maximum problem with these new variables. So let's write that down. We have 1y1, which is y1, plus y2, plus 2y3, I'm looking at that, less than or equal to, right? Because this is the dual problem is a maximum problem, which is equivalent to the original minimum problem. So less than or equal to 2. Okay, so the second row, let's write those coefficients. So minus 2y1 plus y2. Is there going to be a y3 in that inequality? No, because we have a coefficient that is 0. So no y3, but less than or equal to, of course, 3. Then this row, let's write that inequality here. Minus 3y1, right? Plus 1y2 is y2, 1 plus 1 times y3 is y3, less than or equal to 4, of course, right? I hope so far my solution agrees with yours. And of course, we have all these variables should be, the new variables should be non-positive or non-negative. So let's write that down. So y1 greater than or equal to 0, y2 greater than or equal to 0, and y3 greater than or equal to 0. So we're missing one equation, right? That's the objective function for the dual problem. Let me write that right here. And the coefficients come from this last bottom row in the transpose matrix. So I'm going to write it in red. So we have P, right, for the maximum problem. Then we have minus 2y1 plus 2y2 plus 3y3, right? So that's so this whole thing is the dual problem. And so in the previous section 5.2, we learned how to solve a maximum problem using the simplex method. So let's apply that method. And what is the first step in that simplex method to solve the maximum problem, which is this one? The dual problem is the maximum problem. What is the first step? The first step is, of course, write the initial simplex tableau, right? So let's do that like that. So we have P, the objective function variable P, and this is page 9. P, and then remember these are not x1, x2, x3 anymore, so these are y1, y2, y3. And we have 3 constraint inequalities, so we need one slack variable for each one. So we're going to have S1, S2, S3, and of course the right-hand side column. Okay, so let's put the brackets here, and of course the vertical here and the horizontal line here. Okay, so we have in the first inequality, of course, there is no p variable, so the coefficient of p would be 0. Then coefficient of y1 would be 1. For y2 would be 1. For y3 would be 2. For S1, we would have S1 in that inequality to convert it to an equality, so 1, and then no S2 or S3, and of course the right-hand side, which is 2. right? So the second constraint inequality, there is no p, so once again 0. There is a y1 with coefficient -2. There is a y2 with coefficient 1. There is no y3, so the coefficient is 3. And of course, S1 is already used up in the top inequality, so for that, we can't use S1 in the second constraint inequality, but we can use the S2 variables. So for S2, it would be 1. The coefficient of S2 would be 1 in the second constraint inequality. And of course, no S3 there. And the right-hand side, of course, is 3. Okay, so the last inequality. Once again, there's no p variable in this inequality, so the coefficient of it under p column would be 0. But there is a y1, y2, y3. So let's grab these coefficients. -3 for y1, 1, coefficient 1 for y2, coefficient 1 for y3. Is there going to be S1? No. S1 is already used up for converting the first inequality into an equality. So there's no S1 there. How about S2? No again, because S2 was used to convert the second inequality to equality, but S3 is, now we can use S3 to convert this inequality into equality. So 1 under S3, and of course the 4, which is the constant value. Okay, are we done? No, right? What about this objective row? So let's write down the coefficients for that. Remember, because this is a maximum problem, we're going to need to, let me grab my thicker marker here, or we need to rearrange these coefficients, right? So we need to move all those 3 coefficients to the left together with p and set it equal to 0. So p, when you move -2y1 to the left, it becomes positive 2y1. Then -2y2 moving to the left will become -2y2. And of course, positive 3y3, when you move it to the left side, it becomes -3y3. And what do we have left on the right side? Just 0. Okay, so now let's import those coefficients into our objective row here. So under the p column, let me move this up a little bit, so maybe it's better that way, like that. So under the p column here, the coefficient of p in the objective function is 1. So 1, we write that. For y1, we have positive 2. For y2, we have -2. That's under y2. For y3, we have -3. And we don't need slack variables because this is an equation already. So 0, 0, 0, and of course 0 on the right-hand side. Okay? So this is the initial simplex tableau. Now, once again, using the procedure we learned in section 5.2, we're going to have to identify the pivot column. The pivot column is right above, it's the column over the first negative number from the left in the objective row, right? So in the objective row here, right here, the leftmost negative number here is that one. So our pivot column is here. Now look above this negative number. All 3 numbers are positive, right? If we have more than one, just to recap what we already know, if all these numbers are either negative or 0, then we have no solution. We stop and we say no solution. If all these numbers are negative or 0. If you have one positive and the other 2 negative, If you only have one positive number, then the only positive number in the pivot column is going to be the pivot element. Automatically it becomes the pivot element. But in this case, we have more than one positive number, which means we're going to have to calculate the smallest ratio, right? So 2 divided by 1, 3 divided by 1, and of course 4 divided by 1. So clearly this is our smallest ratio. So the one that from which this smallest ratio came from will become our pivot element. So if this was any number other than 1, we would have to convert it to 1. If this was 5, we would multiply this row by 1 over 5. If this number was 3, we would multiply this whole row by 1 over 3. If this was 4, we would multiply this whole row by 1 over 4. If this was 2, we would multiply this whole row by 1 over 2. But it's already 1, so we don't have to do anything to it. Instead, this becomes, so this automatically becomes our pivot row. Right? And we explained that the importance of pivot row is that that is the row, in this case row 1, that is the row we need to use to convert the other numbers in the pivot column to 0. Okay, so we need to use row 1 to convert the 1, and negative 2 to 0. So let's write down the row operations necessary for that. So we have to change this one to 0. This one is in row 2, right? So we're going to have to change row 2. So row 2 is equal to, how are we going to change this 1 to 0? Well, very easy, right? All we need is add a negative 1 to it, and we're going to get this to be 0. But okay, where is the negative 1 coming from? The negative 1 comes from multiplying the pivot row by negative 1 and adding it to row 2. So minus times row 1, which is the pivot row, and we said we're going to have to use the pivot row to make these 0. So minus 1 times row 1 plus the row we're changing, which is row 2. Okay? So that's the row operation for converting this one to 0. How about this? The same thing. All we need is add a negative 1 to this, and we're going to make it 0. Where's the negative 1 coming from? From the same way. Minus 1 times row 1, this time plus row 3, because it's the row 3 that we're changing. This one is in row 3. So row 3 is equal to minus row 1, or minus 1 times row 1, which is the pivot row, plus the row we're changing, row 3. Okay, how are we going to get this negative 2 to be 0? Well, very easy. All we need is to add a positive 2 to this, and we're going to get it to be 0. Where's the positive 2 coming from? The positive 2 can come from multiplying the pivot row by 2 and adding it to row 4, right? So let's do that. So row 4 equals because it's the 4th row that we're going to change. To make this 0, we're going to change the 4th row. So row 4 equals 2 times row 1, because we're going to need a positive 2, right? So 2 times row 1, which is our pivot row, plus the row we're changing, row 4. Okay? So these are the 3 row operations we need to convert the 1, and negative 2 to 0. Okay, so now that we have that, I think the screen is a little bit fuzzy, so let me try to focus it a little bit. Okay, that looks better. All right, so carrying out these row operations, let's do that next. like that. Okay, we have P, Y1, Y2, Y3, S1, S2, S3, and of course the right-hand side column. Like that. So let me see if I can move this a little bit higher. And like that. Okay, so the first row is the pivot row. It's not going to change. So let's write those numbers again here. 0, 1, 1, 2, 1, 0, 0, and 2. Like that. Okay, so the second row is changing according to this row operation. -1 times row 1 plus row 2. Let's do that. -1 times 0 is 0. Plus 0, 0. -1 times 1 is -1. Plus -2, -3. -1 times 1 is -1. Plus +1, it's 0. -1 times 2 is -2 plus 0. -1 times this is -2 plus 0 is -2. Let's see, -1 times 1 is -1 plus 0 -1. Right? I'm just going to double check really quickly to make sure that these are all correct. Yep. So far so good. And then for S2, let me move this down a little bit so you can see it. -1 times 0 is 0. Plus 1 is 1. -1 times 0 is 0. Plus 0, 0. -1 times 2 is -2. Plus 3 is +1. Right? So like that. And now let's move to the second row operation, that one. What are we doing here? We're changing row 3. How? By multiplying row 1, which is the pivot row, by -1, and then adding it to row 3. So, -1 times 0, 0. Plus 0 here in row 3, 0 again. -1, let me move this up a little bit so it's like that. So, like this. So -1 times row 1, -1, plus the -3 in the third row, we get -4. Under Y2, -1 times 1 is -1. Plus this +1 in row 3, we get 0. -1 times 2, that's -2. Plus this +1 in row 3, we get -1. Like that. So -1 times under S1, -1 times 1 is -1. Plus 0, -1. -1 under S2, -1 times 0 is 0. Plus 0, it's again 0. -1 times 0 is 0. Plus 1, 1. -1 times 2 is -2. Plus +4, -2. Plus +4, it's +2. Okay, so we're done with this row operation and this row operation. Now we're moving to this row operation. What is this row operation doing? It's replacing row 4. How? By multiplying row 1 by 2 and adding it to row 4. So let's do that. Row 1 multiply by 2, add to row 4. So 2 times 0, I'm going to have to move this up. Well, because the row 1 isn't changing, it's our pivot row, So let me move this up a little bit so you can only see the fourth row here, because this row didn't change. So it's off the screen from the top of your screen, but you have it right here. So let me highlight it. This is our row 1, which is the pivot row. We're multiplying that row by 2, and then adding it to this row 4, which you can see on the screen. If I didn't do that, you wouldn't be able to see it. It would be off the screen. So hopefully this is better. So 2 times, so we're going to do this. 2 times 0 is 0, plus row 4, which is up here, 1. 2 times 1 is 2, plus this 2 under y1, it's 4. 2 times this 1 under y2, 2 times 1 is 2, plus that, negative 2 is 0. And if it helps, let me write down these variables underneath these. So p, y1, y2, y3, s1, s2, s3, and this is the right-hand side column. Okay, so 2 times under s3, 2 times 2 is 4, plus negative 3 under y3, that's positive 1. 2 times under s1, 2 times 1 is 2, plus the 0, 2. Under S2, 2 times 0 is 0, plus this 0 under S2 is 0 again. Then 2 times 0 for S3, 2 times 0 is 0, plus 0 again, 0. Then for the right-hand side column, we have 2 times 2 times 2 is 4, plus 0, which is the fourth row, it's 4. Okay, so let's double check these very quickly. They all look good. That's good. So all of that looks good. Okay, so are we done? We are done, right? This is done because there are no negative numbers in the objective row. So this is the final tableau. We are done with the row up pivot and row operations. This is the final tableau. Okay, so how are we going to read or interpret the final tableau in order to find the value of the original variables in the minimum problem, x1? Remember, x1, x2, x3? So how are we going to find the values of those from this final tableau? Well, remember, this is a minimum problem. We started with a minimum problem, right? And we found the dual problem, which is an equivalent maximum problem. And then now we have to interpret this final tableau. So for x1, we look under S1. So S1, look under that, it would be 2. So x1 is 2. How about x2? These are the original, again, these are the original minimum variables in the minimum problem, not y1, y2, y3. Okay, so x2 comes from S2, and it's 0, equals to 0. x3, of course, comes from S3, right? In the objective row, that's 0. And how about C? The variable C, oops, let me move this up, like that. So the variable C, again, is here in the corner. For both maximum and minimum problem, it's always that number in here, in the final tableau. So C is equal to 4. Okay, so this is the solution of the original minimum problem. Can we test this? Of course we can test it. All right, so let's do that. So let us remind ourselves what the equation, objective function was. So testing the solution we have. We have the original objective function, which was c equals 2x1 plus 3x2 plus 4x3. So let's plug in. So if we plug in for x1, x2, x3 with these values, we should get 4 for c. Let's see, do we get that? So c equals 2 times 2 plus 3 times 0 plus 4 times 0. So this is just 0. That's just 0. 2 times 2 is 4, which is equal to the value that we found from the tableau. So it checks out. Okay, so this brings us to the conclusion of another section. This will be the end of the simplex method. So please and the final exam is going to be cumulative. So please make sure that you remember this for the upcoming exam 2 and also for the final exam. All right, thank you for persisting through this another video. And for now, have a nice day, and I'll see you again next time.